Good afternoon, everyone. So, we meet again on another live session. Welcome to Rao's IAS YouTube channel. This is a platform that we are using for using uh, YouTube as a medium for sharing more information, guys. This is a way how we are able to communicate on a lot of issues of current affairs, and this is a platform that makes it, makes us available for the students who are preparing for civil services from all platforms, from all corners of the world. So let us start, guys. So today's topic of discussion is on Nobel Prize for Physics that has been recently convened for the year 2023. And if I start from a certain section, all of you understand that this year the Nobel Prize have been given to three physicists, in which one of them is a woman physicist. She is the fifth lady so far to receive a Nobel Prize on physics. I'll start from her. Her name is Annie Hewler. Then we has the, Cross is the name that you can remember. And Pierre Agostini. These are the three physicists who have received the Nobel Prize. And the purpose for which they have received the Nobel Prize are basically the developments that they have done. The developments that, or the experimental methods that they have created to generate attosecond pulses. To generate attosecond pulse. So with the help of this attosecond pulse generation, we are now capable of performing attosecond spectroscopy. Now we'll see what is attosecond spectroscopy with the help of this phenomena of attoseconds, how they were able to generate it, and what is the significance of this particular achievement, for the rest of mankind. So let us start, guys. So these are the names of the scientists who have been awarded the Nobel Prize for Physics. Now, before I start with the concept of attoseconds, and we dive into the area how these scientists were able to invent or develop this particular technique. Let us first understand what is the concept of measuring time for us. How do we measure time in general? So, all of you have seen this particular pendulum that has been oscillating. All of you guys can easily observe this pendulum oscillating here. Now, if I ask you, if I suppose you must have noticed that the old traditional pendulum clock, it has pendulum oscillating from these two locations. Once the pendulum goes here, then in the other moment the pendulum goes on the other side, and that's how the time moves. Now, if I tell you that the time period, the period what it takes to completely oscillate from one extreme position to the extreme to another extreme position, let me define it here, guys. Please pay attention. So if I consider this as a pendulum, the center position, this particular center position is the mean position, guys. This is considered as the mean position of the pendulum. Okay, this is the mean position of the pendulum, and as the pendulum you guys can see oscillating, if I put a certain mark, it is oscillating from these two points. It is oscillating from these two. The bob is moving, the center of the bob has been moving around these 2 points. So we call them extreme positions. We call this as extreme positions. So technically, the pendulum is going to oscillate from mean position to one extreme, then to another extreme, and then keeps oscillating between these two extreme positions. Now, what if I tell you that as the pendulum is oscillating between these two extreme positions, if I say that one complete oscillation, that means movement from one complete extreme position back to another extreme position, and then again back to the same extreme position. So if I tell you that one complete oscillation of the pendulum, it takes 2 seconds. If I say that it takes 2 seconds to complete one entire oscillation of the pendulum. So if I say that it takes 2 seconds to complete one entire oscillation, that means it is moving from one extreme to another extreme and takes 2 seconds to move from one extreme to another extreme and then goes back to the same extreme in 2 seconds. So if I ask you, what is the minimum time that you can calculate by using this pendulum clock? So you will say that 1 second is the minimum time. Why? Because if it goes from one extreme to the other extreme in 1 second and comes back from one extreme to the another extreme in another 1 second, it's obvious. So 2 seconds is the total time period, and half of this oscillation you can time. So you will say that 1 second is the minimum time that one can calculate by using this pendulum clock, because 2 seconds it takes to complete one entire oscillation. So half oscillation means 1 second. So 1 second becomes the shortest time that you can calculate by using this particular pendulum clock. Now, let's say if I use this pendulum clock to find or to check the speed of the fastest person on earth. You guys have heard of Usain Bolt. So Usain Bolt is able to run a 100-meter sprint in a span of 9.58 seconds. He can run a 100-meter sprint in a span of 9.58 seconds. So like if I use the same pendulum clock to measure the speed or measure the time taken by Usain Bolt to cover 100 meters. So because the shortest time that we could measure in this clock is 1 second, that is why I can conveniently measure 9 seconds of the time. 9 seconds of the time I can conveniently measure by using the same pendulum clock. But how about the 0.58 seconds? How difficult it would be for us to calculate 0.56 seconds, because we would not know where this pendulum is going to be in a time frame which is less than 1 second. So where this pendulum is going to be in a time frame less than 1 second, and that is why it would be impossible for us to find the exact time what Usain Bolt will take to run 100-meter sprint. So of course you guys can understand this is the maximum limitation for this kind of clock. But now let's say if I give you another pendulum, and suppose in this case the pendulum is oscillating from the extreme position, let's say 100 times in 1 second. Like this one was oscillating, one oscillation, it was taking 2 seconds, right? One oscillation in 2 seconds. This time suppose I replace this pendulum and let's say it is able to rotate, it is able to oscillate 100 times in 1 second. That means I can now break the entire 1 second into 100 different oscillations. In fact, technically, if it is moving 100 times, that means I take half a oscillation and I'll be able to break 1 second into 200 times, because one oscillation is one to and fro motion. So if it is taking 100 to and fro motion, I can divide by 2 and I can multiply it by 2 and I can take 200 half motions, half oscillations, and then I can easily break 1 second into 200 periods. I can break into 200 periods, and now I can easily calculate where this particular, or I can easily calculate how much is going to be the time taken in one complete oscillation or half an oscillation. So I can break 1 second into two different time frames, and we can easily calculate accurately how 1/100th or 2/100th of a second, how much time will it take. We'll be able to measure it like this. I hope you're able to understand. So by giving you a bigger pendulum that can oscillate multiple number of times in a given time frame or in 1 second, we can obviously improve our measurement capability. We can improve our capability of measuring time. So if I take a pendulum that can oscillate once in 1 second, it can only help us to calculate 1 second. If I give a pendulum that can oscillate twice in 1 second, you can break 1 second in half. If I give a pendulum that can rotate, that can oscillate 4 times in 1 second, we can break 1 second into 4 times, and likewise quarter of a second, then 1/5 of a second, then 1/6 of a second. Likewise, we can start breaking down time in this way, the number of times the oscillation happens. I hope you guys are able to understand. So this is how the concept of time measurement works. Now, just to give you a small example here, look at this. These two images are the images of hummingbird. I'm taking the same analogy which has been used in the Nobel Prize, press release also. If you look at this image on the left side, if you look at this image on, like technically on my right side here, you will notice that here the hummingbird is clearly visible, but the wings of the hummingbird are not visible at all. Actually, hummingbird has a tendency of flapping her wings up to 80 times in 1 second. That means 80 times it is flapping her wings in 1 second. So if you want to see the hummingbird clearly, human eyes cannot notice the difference. Human eyes will never be able to see the entire flapping of the wings very clearly, because our eyes cannot, register this much of information in such a short span, 80 times in 1 second. But if you take this image with a very sophisticated camera that can easily manage to take 80 images in 1 second, it can easily you can control the shutter 80 times in 1 second. That means it is basically breaking 80 different frames it is taking in 1 second. So with that kind of a camera, you can actually see a much clearer image of the wings. If you can see in this image, the wings are very clearly visible. So this is possible only when you increase the frame rate of the camera. So it is possible for us with the sophisticated imaging techniques that we have, manually we can adjust them electronically also, and we are able to register a higher frame rate of observation. So we are able to break 1 second in 80 frames in this case, let's assume. So it is able to take 80 different frames in just 1 second. That means the clock here, which is running this particular camera, is able to create 80 different breakouts of 1 second. I hope you're able to understand. So this basically improves the capability, our own capability of observing events happening 1/80th time of a second. I hope you're able to understand. Now, suppose, so when it comes to observing objects like a hummingbird, it is possible for us to simply use a camera which is capable of taking images, or which is capable of capturing 80 frames, which is capable of capturing 80 frames per second, which is capable of capturing 80 frames per second. FPS, I'll simply write it down, right? 80 frames per second. And that means this camera is capable of breaking 1 second into 80 different time periods, 80 different time periods, right? And that's how this image can be easily captured. But now let's dive into the world of quantum physics here. When you talk about such events, it is possible for us to use conventional photography and map these kind of events. But now, if you talk about electrons, I hope you all understand that for any atom, at the center of an atom, we have got the nucleus, and the nucleus is made up of protons and neutrons, right? And around this nucleus, we have got a cloud of negatively charged particles called the electrons. And see guys, these electrons are also consistently revolving. These electrons are also consistently revolving around the nucleus, right? Now the speed at which the electrons are revolving is very high. It is so high that even if I use a clock, which is having 1000 oscillations in 1 second, that means it is having 1,000th of a second. It is capable of breaking down 1 second into 1000 units, 1,000th of a second. Even this clock will not be able to see the electrons moving. In fact, if I go up to 1 microsecond, 1 microsecond is 1 millionth of a second. That means dividing 1 second into 1 million parts. Even a microsecond is also not capable of observing a movement of the electron revolving around the nucleus. In fact, if I go even 1000 times smaller than this, even break time 1 second into even more 1000 intervals, we call it nanoseconds. If I go into nanoseconds as well, which is 1 billionth of a second, that means you are breaking 1 second into 1 billion time intervals. I'm not making 9 zeros after this, but I hope you can understand. This is 1 billionth of a second, nanosecond. Even this nanosecond is also not capable of visualizing the movement or the revolution of electrons. That means electrons have been moving so quickly that we are not in a position to see electrons even by using a sophisticated clock that can measure nanosecond time. So how are we able to see? How will we be able to observe the movement of the electrons? How will we be able to, and if you are not able to observe the movement of electrons, you guys can understand everything that is happening around us is happening through electrons, guys. All kinds of chemical reaction that goes inside the body, all kinds of chemistry that we see around us, all kinds of materials that we see around us, they are basically because of the chemical properties of the elements. And the chemical properties are shaped by the electrons, by the interactions of the electrons. The common salt that we eat, it is nothing but NaCl. It's a chemical reaction between nitrogen and between sodium and chlorine, right? The oxygen that we breathe in, it's a chemical interaction between two atoms of oxygen, O2 they eventually become, and we breathe in that oxygen. So what I'm saying is that to understand the real nature of extremely fast moving objects, it is impossible to time them, it is impossible to take their images, it is impossible to observe their interactions even with a clock that is capable of measuring nanoseconds. It is impossible for us to know their true nature, their true behavior, even with a clock that is capable of measuring 1 billionth of a second, right? So now let's talk about the achievement that has been made by these three scientists in the world of physics. So what happened lately, guys? If you talk about nanosecond is something which is 1 billionth of a second. If I go 1,000 times further deep into nanosecond, that means I break 1 second into 10 to the power 12 different oscillations. If I break 1 second into 10 to the power 12, we call it picosecond. Picosecond is something which is 1,000 times shorter or 1,000 times smaller than a nanosecond. That means the duration of 1 picosecond is going to be 1,000 times shorter than 1 nanosecond. Nanosecond itself is 1 billionth of a second. Picosecond is 10 to the power 12. That means it is 1 trillionth of a second. 1 trillionth of a second. I hope you guys can understand, right? So when you break down 1 second into 1 trillion different parts, you get a picosecond. But you'll be surprised to know even picosecond is also not enough to measure or to observe the movement of electrons, to observe the molecular interactions. We have to dive even deeper, and then we got the femtosecond. Femtosecond is basically the time where 1 second is broken into 10 to the power 15. 10 to the power 15 different intervals. It is broken into 10 to the power 15 different intervals. Technically, it is 1,000 times smaller than a picosecond. So when you go 1,000 times smaller than a picosecond, you enter into the domain of femtosecond, guys. And femtosecond itself is such a major achievement in the world of physics that the 2018 Nobel Prize went to the scientist for discovering femtosecond spectroscopy. Femtosecond spectroscopy. So they were able to time events occurring in a span of just a femtosecond. And they were able to take images of the events occurring in a femtosecond, and that basically made them get the Nobel Prize of 2018. I hope you're able to understand. But you know what, guys? Femtosecond can help us observe a lot of molecular phenomena. But if you want to observe the movement of the electrons, the flow of the electrons, it is still not possible to observe them with femtosecond. So femtosecond was not the possibility which we needed. We needed to go even beyond that. And that is where we introduce the attosecond scale. If you talk about the attosecond scale, attosecond is 10 to the power 18, guys. It is basically breaking 1 second into 10 to the power 18 different intervals. 10 to the power 18 different intervals. That means it is technically breaking 1 nanosecond into another 1 billionth of a nanosecond. So it's basically 10 to the power 18. It is breaking 1 second into another billion small components. So this is called attosecond. And attosecond is the reason why these scientists have got the Nobel Prize. These scientists have been able to develop a technique through which you can time an event occurring in an attosecond. And this type of events are so small that otherwise we never had a possibility of developing this. But in the late 1980s and the early 2000s, these three scientists worked out and they were able to develop possible techniques through which you can time an attosecond event. And then with the help of those attosecond events, they were able to create images of the events occurring during that time. Now, of course, attosecond event, it is not humanly possible for us to visualize. Attosecond events are occurring somewhere very deep inside our chemicals, very deep inside our atoms, where the electron has been revolving around the nucleus, where the electron interacts with other elements and merges and creates new kinds of bonding patterns, create new kinds of compounds. All these events may be occurring at that scale. And with the help of development of attosecond, now a new window of opportunity opens up in the world of science. And they truly deserve the Nobel Prize for this. Now, how exactly they develop this technique? Now, from UPSC point of view, it's not very relevant to know the nitty-gritty of the techniques. But yes, I'll try to still explain the things so that a non-science and a science student, both of them are able to understand. So let's dive into the basic concepts here. So in this particular scale, I've shared that what is a millisecond? A millisecond is 1,000th of a second. When you break down 1 second into 1,000 interval, you get a millisecond. Millisecond events are like a housefly flapping her wings. So when a housefly is flapping her wings, it is equal to 1 millisecond. When you talk about microsecond, 10 to the power minus 6, I hope you understand 1 millionth of a second. This is basically a length of time where of a high speed strobe light flash. So normally when we see a light flashing, high speed strobe light flashing, it is a microsecond event. Then nanoseconds are the kind of events where we see fluorescence, right? Molecular fluorescence. Picosecond is 10 to the power minus 12, 1 trillionth of a second. This is switching time of the world's fastest transistor right now. So right now the fastest electronics that we have made, they run at a scale of picoseconds. So they are able to turn on and off in picoseconds, right? I hope it should build in your mind automatically, guys. The moment when you know picosecond has now been, we have been able to shift 1 millionth smaller than a picosecond, attosecond based transistors will be able to develop even faster electronics, right? Femtosecond is pulse width of the world's fastest lasers. I'm not discussing lasers here, guys. Lasers, we can have a different discussion sometime else. You can just remember lasers are nothing but high energy light, guys. Okay, attoseconds are the ones which is the shortest measurable time that the scientists have been able to develop now, and that is what this Nobel Prize deserves, right? We'll talk about the other scale later on. So what my point here is, so how these people were able to develop this attosecond pulse generator and how this attosecond pulse generator can help us in taking images. So you guys have understood the entire idea behind attosecond. You guys have understood how these attoseconds can help us to visualize very small occurring events. So here I'll go a little technical, and I'll try to maintain my boundaries here so that a non-science student is not able to get detached from the concept here. So basically the idea is, see, so you all understood that in a normal clock we have a pendulum, and the pendulum keeps oscillating, and with the oscillation of the pendulum we are able to measure the different time frames, right? So more number of oscillations, more number of oscillations, quicker, more and more shorter time you can calculate. And if the number of oscillations keeps increasing, you can obviously calculate even shorter or smaller events, right? You guys have understood. So now let's say if you talk about a pendulum which is able to oscillate, if you talk about a pendulum that is able to oscillate, let's say 100 times in 1 second. So you can easily break 1 second into 100 intervals. If I tell you that there is a possible pendulum which is capable of oscillating, let's say billion times in 1 second, you'll be able to break 1 second into billion oscillations. And similarly, if I tell you that there is a pendulum that can oscillate 10 to the power 15 times in 1 second, then that means you can break down the entire 1 second into 10 to the power 15 oscillations. You guys can understand this. So how is it possible to really create pendulums of such a nature? So pendulums cannot be used to create the basis for these smaller seconds. But you know what, guys, if you consider light is nothing but a wave, and as you guys can see, this wave traveling through this particular medium, traveling through this particular space, it is having a peak. All of you know that the peak of the laser, a peak of the light, we call it the crest, right? And this particular valley that is created, the other end of the wave, we call it the trough. So when you see the light oscillating between crest and trough, don't you think, or doesn't it resemble like the same kind of oscillation that we see in a pendulum? Like if I put the pendulum like this and make it oscillate up and down, then don't you think it will resemble how the light waves is also oscillating? So the photon particles or the light wave which is traveling, it is simply carrying the particles move up and down like this. So if I consider the time it takes for the wave to reach the crest and also the time it takes for the wave to reach the trough, and suppose if this time gap where the wave touches the peak and the wave touches the trough, between the peak and the trough, if I measure, let's suppose I find out that between the peak and trough we are able to see, let's say 1 million oscillations. We are able to see 1 million oscillations in 1 second. That means the frequency, that means the frequency of this wave is going to be of such a nature that in 1 second 1 million oscillations of peak and trough are being created. Then don't you think this particular wave can be used as a pendulum? Or I'm using the word pendulum as a figure of speech here, guys. So we can use this particular wave as a pendulum to create a kind of a clock that can observe 1 millionth of a second. We can break 1 second into 1 billion components. Similarly, if I tell you that there is a wave possible that can have a kind of oscillations from peak to trough, which goes up to 10 to the power 9 times in 1 second, that means this wave can easily help us to break 1 second into 1 billion components, because that will behave like an oscillatory component. And what if I tell you that there is a possibility of creating a wave which is capable of breaking, which is capable of oscillating from peak to trough 10 to the power 15 times? That means you can actually break 1 second into 10 to the power 15 different oscillations. And what is that single oscillation? What is that single period would be known as? It's nothing but 10 to the power 15 is femtosecond. If it breaks 10 to the power 12 times, it will be picosecond. If it breaks 10 to the power 9 times, it will be nanosecond. And suppose if it breaks 10 to the power 6 times, it will be milliseconds. Sorry, microseconds. Milliseconds 10 to the power 1000 times, right? So you guys can understand by simply changing the focus from a conventional mechanical or conventional mechanical pendulum and changing the entire frame into a wave that can oscillate from peak to trough at a very high frequency, we can easily shift into, or we can easily dive into creating much more sophisticated methods of creating a time or a time calculation scale, right? So when it comes to using light as a scale for oscillations, scientists were able to reach up to femtosecond level of observations. Scientists were able to reach up to the oscillations of femtosecond levels. So it was possible for us to create femtosecond scale of observations by using the simple principle of oscillating wave of light from one peak to trough, one peak to trough. So light, you can easily take a hint like this, that when you consider light, when you consider any wave traveling, light has a frequency up to exahertz. Exahertz means, let's not go into there, because in that way I have to talk about frequency, terahertz, gigahertz, terahertz, and then eventually going to petahertz and terahertz, petahertz and exahertz. So we don't have to get there, but you can remember that light has a certain frequency where it can easily stretch our possibility of observing time up to the scale of femtoseconds, up to a scale of femtoseconds. So we can observe time up to a scale of femtoseconds by using light as the medium of observation. But you know what? It was considered as the maximum that we can reach. So scientists were always under this impression that femtosecond is probably the smallest time that we can measure, until these three scientists came into picture. So femtosecond was always the smallest time. But then what happened in the year 1987, to be precise, Annie Hewler, she came up, Annie Hewler, right? She came up with an idea that we can actually create oscillations. We can actually create oscillations even smaller. We can create even smaller oscillation. We can create even smaller, shorter wavelengths. Which can create multiple oscillations beyond the scale of femtoseconds. And she was able to demonstrate this. She was able to demonstrate this for the first time in 1987. Where, now how was she able to do it? I don't think that's very relevant from UPSC point of view, but you can just imagine that she used a certain laser that was made to pass around a gas, and then she observed how the energy of that laser excited the electrons, and as the electrons started moving, it created a kind of a wave pattern which she observed. And by interfering all those wave patterns, she was able to create a kind of a resultant wave that happened to create multiple oscillations even beyond femtoseconds, right? But that part I don't think is very relevant. So you can just remember that now it is possible for us to observe any kind of scientific event, any kind of natural event at a scale of 10 to the power minus 18 times of a second, right? And this technique was first developed by Annie Hewler, and eventually the other two scientists, they used this technique, developed it into an actual spectroscopy. That means they were able to observe these events, and eventually when they observed these events in such a small time frame, they were also able to create an image that they were able to create. They were also able to create an image of the same events occurring in a shorter time frame. So I'm not saying that at this particular time frame you can observe the oscillations of electrons around the nucleus. It is not like you can observe oscillations of electrons, you can take images of electrons. I'm not suggesting that. But yes, by taking each and every photograph in a flash of attoseconds, it is definitely possible for us to observe the movement of the electrons. See, these particles are so small. These particles are so small that we never had any imaging technique possible for us which could help us to observe objects at such a small scale. But this is definitely one achievement that we have now, which enables us to take images in such a short time frame that we can obviously observe the trajectory in which the electrons have been flowing. We can definitely observe the trajectory that the electron takes. And by even knowing the trajectory that the electron takes, we can definitely learn a lot about atoms interaction and making a molecule, about molecular interaction with other molecules, how chemical reactivity really turns out and creates new kinds of elements. All these possibilities are there. I hope you guys are able to understand. So from UPSC perspective, I believe this much should be enough. But when you talk about applications, of this particular concept, this is something which I believe UPSC should not miss out. This is one area where we have definitely made a lot of achievements because of their hard work and innovation. So one application that I believe is very important is the field of atomic and molecular research. We are now in a position to observe how the molecules, how the atoms are really interacting with each other. We can obviously observe the flow of electrons really occurring within an atom, how the flow of electrons happens within different molecules. With the help of this technique, we can also develop better disease diagnostic tools. Like, say for example, you understand there is a disease cancer. Now cancer normally occurs when there is an uncontrolled multiplication of uncontrolled multiplication of infected cells. Now whenever any cell get infected and suppose it turns into a cancerous cell, there will have to be some kind of chemical formation, and there have to be some kind of secretion of our antibodies which will try to kill those chemicals, and because of their inability, the infectious cell starts multiplying. So all these events can be very closely observed with the help of attosecond spectroscopy. Spectroscopy is basically a technique of imaging where we use events happening in an attosecond and we are trying to project them on a screen or any kind of representation. Spectroscopy, right? Faster electronics in computers, like you guys know already, the current transistor, the fastest of the transistors that we have developed so far, they work in a scale of picoseconds, right? They work in a scale of picoseconds. That means they can have 10 to the power 12. 1 trillion operations it may be able to perform. 1 trillionth of a second it may be able to react. So in 1 second, it may be able to give 1 trillion, outputs. It may be able to give 1 trillion outputs because it is able to react, turn on and off in 1 picosecond. Right? This is 1 trillionth of a second, sorry. So this is 1 picosecond, which is 1 trillionth of the second equal to 1 picosecond, right? All right. So you can also see it in a way that in 1 second, a transistor having this particular efficiency of turning on and off can produce 1 trillion outputs in 1 second, right? 1 trillion times it can turn on and off in 1 second. But imagine if we are able to create observations, if we are able to observe the world that is even million times smaller than a picosecond. We are going million times smaller, guys. 10 to the power minus 18 seconds. It is 1 million times smaller than a picosecond. Then just imagine if you are able to observe the world at this scale, we can obviously create technology. We can obviously create, chip which can go up to a scale of attoseconds. And suppose if you are able to develop transistors that can respond in an attosecond, it is fairly obvious that we can create much faster electronics. So this was a small discussion that we had to do on the topic of the Nobel Prize for Physics. We'll be meeting very soon again to discuss the Nobel Prize on Chemistry, right? And with this, I conclude this discussion. Looking at the questions, is it possible? See, Ravikant has asked the question that is it possible for us to go further from attosecond? Mathematically, yes. Mathematically, yes. Just to answer Ravikant's question, see, when you talk about waves, mathematically, yes, it is possible to create any kind of wave output. Like when you talk about light, the maximum range that we could reach was femtosecond, right? Maximum that we could reach was femtosecond. But is it possible to go beyond? Yes, it is possible mathematically. We simply have to find possibilities of creating a wave that can have that many number of oscillations in 1 second. So yes, it is possible, but to develop a kind of a wave, like right now, they have been able to achieve this because they saw that when they were able to make an infrared light, when they were able to make an infrared laser travel through an argon medium. An argon is a gas, it's an inert gas. When they were able to make this particular infrared light pass through an argon medium, they observed the electrons of argon getting excited and then fusing into other atoms and then eventually creating a wave pattern. They were able to create an interference pattern that could have an attosecond pulse. It could create a peak and trough in attosecond range. But is it possible to go even further? Mathematically, yes. But practically, right now, this is the maximum scale that we have reached, right? So it may be possible in future, if we are able to develop further in this area, we may be able to go even further. And if we go even further, then taking the real image of an electron maybe at one time may be really possible, guys. I hope you guys have been able to understand. And I hope you like the discussion. You can give your comments, and wherever you feel, you can add some more suggestions so that we can improve in the next time, in the next discussion when we meet. Thank you, guys. That will be everything in this video. Thank you.